Okay, so last class we talked about stochastic gradient descent and the problem that it was trying to solve, which is that sometimes even computing the gradient itself is too expensive. So we want to find ways around that. Okay. And we also saw that stochastic gradient descent still works for convex functions. Okay. And finally, I briefly alluded to it, but you can basically generalize all of the other things also to stochastic gradient descent. Like, if I don't have gradients, but I have subgradients, I can still do a stochastic version of it where I assume I have an estimator for the subgradient instead of the actual gradient. And I can also implement acceleration, adaptive step sizes, and all of the other tricks that we have. Okay. And what I want to do today is first kind of, some general remarks on optimization beyond gradient descent. Okay. And then we will move on to kind of the next topic, which is closely connected to optimization, but somewhat different, which is online learning. Okay. So again, we're going to approach online learning from the perspective of online optimization, but you can pretty much think of it as kind of a subfield of learning, as we will see. Okay. So first, also a couple of important announcements. Assignment 1 will be posted today on Gradescope. Okay, it should be posted tonight, roughly 10 p.m. and is due exactly 1 week from now, which is April 22nd at 10 p.m. Okay. And you will submit the assignment also on Gradescope. When you're submitting, make sure that you indicate your section accordingly. There are 3 sections for this class: Section 1, Section 90, and Section 81. Section 1, Section 91, and Section 80. Please mark it accordingly because each section will be, the final grades will be assigned separately. Okay. So please mark your section under submission. Okay, and the assignment basically covers the first 4 lectures. All right. And also okay, that's all about the announcements. Right. Oh, let's see. Right. Any questions about the assignment? We'll have office hours of the TA and E. Today my office hours from 3 to 4, and I'll have one more officer before the assignment is due next Monday from 2 to 3. Okay. All right. So let's go back to what we were talking. 3 or 4 lectures ago, we started out by saying learning can be viewed in many contexts as optimization by looking at empirical risk minimization. And there, we've mainly been looking at what we call unconstrained optimization. Okay. And here, unconstrained meant that, you had some function f, and we wanted to find a point that minimizes the function over the entire domain. We did not have any specific constraint on, where the minimizer could be. But sometimes you might have additional constraints on the optimization problem. And that leads to what's called the constrained optimization problem, where your goal, once again, is to minimize a function f of x, but now you're also given some set C. And you're only looking for the minimizer within this set C. Okay, the set C could be like, okay, maybe I don't want my minimizer to be too far away from the origin. Maybe I want my minimizer's entries to be non-negative, and any other constraints that you can think of. Okay. And for the unconstrained case, we had this very nice general method, right? But let's say this is my set C. And if I want to do minimization over this set, what can I do? Okay, so when there was no constraint, we could just do gradient descent, like, take a point X, move along the gradient, and then keep repeating this. And at the very least, it gave us some guarantees in the case of convex functions. And even in general, it was a good heuristic to run. Okay? But if you're in a constraint set, which is in the constraint setting where you have a hard constraint, and maybe this is your point xt, and you take a gradient step, maybe you go outside the set. Right? So how can you adapt gradient descent in this case? Is there a version of gradient descent to handle constrained optimization? Any guesses, any suggestions? Well, you can still try something like gradient descent. You just take a step along the gradient. But if the point is inside the set, you're fine. You're kind of doing the same thing as you did before. But if you stepped out of the set, what can you do? You can try and step back into the set, right? So if I go out, I want to come back into the set. Okay. And if you want to come back into the set, which point should I go back to? Yeah. Right. So that's a good guess. Although I would say, maybe it's clear from this picture. Actually, let me draw the same picture in a little different way. Right. So let's say this is where I went to. Okay. So the suggestion was, why don't you go back to the point on this line where you kind of went out of this set? That's a good suggestion. Any other suggestions? Yeah. Right, so you can either go here, or maybe it also makes sense to find the closest point. So that way I'm kind of, moving away as little as possible from gradient descent, right? So there are problems where what you said is actually the better thing to do. But there are also, in general, this is a better alternative because, you can essentially argue as you would for gradient descent for many interesting cases, okay? So let me say, right? So you move to a point like, let me call this intermediate point xt plus 1 prime. I kind of compute the gradient step. But then if I'm going outside the set, move to the closest point to x prime t plus 1 in C. Okay. And what is this operation of finding the closest point in a set called? Have you heard this, or have you seen such an yeah, exactly. It's called a projection. Okay. So this method is called projected gradient descent. Okay. So you first define the projection of any point X as the closest point in my set. Among all the points in my set, what point is closest to this? Okay, and once again, we are measuring distance in the L2 norm because that's the most typical scenario, but you get very interesting algorithms by looking at other norms for many different problems. Okay, and projected gradient descent is basically very similar to gradient descent. I start from an arbitrary initialization point, x0, and I do a gradient step as before, but after I compute, take the step along the negative of the gradient, I project back onto the set. Okay. All right, so this is one popular way to handle constrained optimization. Okay, this is assuming here in gradient descent, we assume that we could compute the gradient. That was the only assumption, right? Assume we can compute gradient. Okay, and now we are also assuming, in addition to computing the gradient, we are also assuming that we can compute projection onto C. Okay, so we have to be able to solve this minimization problem. How do we solve it? That could itself be an optimization problem that you have to solve one way or the other. But let's say you can do that, then you can mimic gradient descent in this more general constrained optimization setting. Okay. And you might wonder, like, when does this work? For gradient descent, we had some very nice guarantees. Do those guarantees actually extend? Luckily, most of the guarantees and analysis, for GD, stochastic gradient descent, Nestrov's accelerated gradient descent, etc., work. For projected gradient descent, as long as C is convex. Okay. So, just as we extended gradient descent to constraint optimization, we can also extend stochastic gradient descent, right? Just take a step along your estimator for the gradient, project back. You can also do Nesterov's accelerated gradient descent, basically do Nesterov step and then project back. Okay. And as long as your set C isn't too crazy, the same bounds work. So convex just means that for any 2 points in the set, the line segment connecting them is also inside the set. It's like, you have to be completely inside the set for any line segment, right? So this is convex. Okay, whereas something like this is not convex. Okay, so this is not convex because I have a point here and here. This line segment between the two is not within the set. Okay, there is a portion where it's going out. So this is not convex. Okay. All right. So projected gradient descent is one way to handle constraint optimization, but there are also other ways, I won't survey all of them, but let me just say a few words about two of the most important ones. In general, you can formulate this question of convex optimization. Okay, so convex optimization is okay, so f is a convex function. So I have some convex function f, from in d dimensions to a real number, and I want to minimize that convex optimization over a convex set. Okay, so this is a very powerful class of problems. So if you have heard the term linear programming, that would be a special case of convex optimization. If you have heard of the term semi-definite programming, that would also be a special case of convex optimization. Okay, so these are all special cases of this most general framework, which is convex optimization. Okay. So if you're given a general convex optimization problem, you can solve it reasonably well if you can compute the gradient and you can compute the projection operation, right? As I said, all of the guarantees that we have for gradient descent, SGD, they all work in this setting. Pretty much nothing about the analysis needs to change. That's kind of a very nice coincidence that even for general convex optimization, where I have a convex set, I'm in the constrained setting, nothing really needs to change in your analysis for what we did so far. Okay. But if you're given a little bit more power, you can solve the problem substantially faster. Okay. So let me say a couple of words about that. And okay. If we are given a separation oracle for C, okay? So I'll define what the separation oracle means, but let's first parse the bound, right? This is saying we can solve the convex optimization problems in time, which is polynomial in the dimension, which is D, okay? And the runtime is now only logarithmic in the precision epsilon that you want, okay? So gradient descent was very good, but its runtime was like, if I wanted to get epsilon accuracy, I had to run it for basically 1/square root of epsilon, right? So sometimes you might have to solve the problem to very good accuracy, and their gradient descent would be way too slow. Whereas these more powerful methods can do much better in terms of the final error guarantee that you get, but have a dependence on the dimension. Okay, it's a trade-off, whether you want better performance in the precision that you're shooting for or in the dimension. Okay. Any questions? Okay. So what is the separation oracle? So this notion of oracles is actually very important in optimization because they give you a way to abstract away what you need to kind of implement an algorithm, right? So for gradient descent, you can think of it as, it's an algorithm which needs a gradient oracle. anything that can compute the gradient, I can just use it in a black box way and run gradient descent. Okay. Separation oracle is similar, where say, okay, so this is a convex set C. Separation oracle just means that given a point X, okay, either say that the point X is already in the set C, okay, or no, output a hyperplane which separates the two. Okay. So either the point is inside the set, then you just say, okay, the point is actually inside my set C. But if it's outside, I want you to basically tell me a line, okay, so that the set C is on one side and the point X is on the other side. So like a separating line is, one side is C, the other side is the point X. Okay. So as long as I can compute such a separating line, I'm good. That's the only thing that you need for running these meta algorithms for convex optimization. Okay. And in many cases, separation oracle can be done, you can implement a separation oracle much more efficiently than even computing the gradient or the projection. Okay. So if you want to look it up later, you should look up this beautiful method called the ellipsoid algorithm. Okay. So So sometimes, you might not even be able to write down the set fully, let alone computing the projection, but you might be able to compute the separation oracle. Okay. And so these algorithms, ellipsoid algorithm and related versions like the interior point methods are very important in operations research, optimization, and as I said, for linear programming and semi-definite programming. Okay. We're not going to touch upon these things, but if you're interested, I can give you some pointers. Okay. All right. And even for gradient descent, we are not covering many things. So let me just enumerate many of the things that we are not covering. So we did not cover different norms for steepest descent. So in all of our presentations, we said gradient descent is basically you're taking a step along the direction of steepest descent. But we measure the distance in terms of the L2 metric. If you change the metric, you get a whole class of algorithms. And there's a whole, rich theory of them, which we are not touching upon. The other thing we did not cover, which is actually quite important in practice, is change the landscape. Okay. Meaning, even if I'm running gradient descent to minimize a function, sometimes it helps to not work directly with the function that you're trying to minimize, but kind of work with a surrogate function which has a nicer landscape. Okay. So maybe my crazy function is like this. Okay. The optimizer is somewhere, the minimizer is here, but maybe I can compute another function which is nicer, but also has the same minimizer. If you could do this, you'd rather run gradient descent on this blue function than the black curve, right? Because black curve is not convex. It can, let's say, maybe it's even more crazy. This is surrogate loss functions. Okay, once again, there's a theory of surrogate loss functions, or how you can change the landscape while keeping the same minimizer so that gradient descent can run better. Okay. And there are things called mirror descent. Okay, so mirror descent basically just means that you can reparameterize the problem. Okay, so maybe I do some variable change in your function. If you do a variable change, your gradient changes, and your gradient descent can be a completely different algorithm after you do a variable change. Okay. So changing variables and doing gradient descent. This is also something that we didn't check. And there are lots of heuristics that are still based on sound theory for speeding up gradient descent in practice. Okay, you can do some things called gradient clipping, for example. You only do gradient descent steps if the coordinates are not kind of overshooting too much. And we briefly touched upon adaptive learning rates. There are things like renormalization and many, many other things. Okay, so even though we spent several lectures on gradient descent and its variance, there's still a lot of stuff that's extremely important in practice that we're not touching upon. Okay, but hopefully at least you got a sense of what this basic method is, what you need to run this basic method, and how to adapt it if you need. Okay, any questions about gradient descent and its variance so far? Okay, if not, we can go on to our next sort of big topic, which is online learning. Okay. All right. So what is online learning? Online learning is learning where if you think of a one-line summary of what online learning is, it's just learning where you do not see all of the data at once. Okay. Meaning typically when we talked about machine learning and empirical risk minimization, we said, okay, you have your database in your hand, and then you're trying to build a predictive model, right? In online learning, you should basically think of this scenario where every day you're collecting more and more data, and you want to refine your model every day. Instead of starting from scratch every day, or just using the same model, as you collect more and more data. Okay, so online learning is trying to mitigate or sort of model this real world scenario. Can you think of examples where you might be in a situation where you're collecting more and more data, but at the same time, even in the process of collecting in the intermediate time steps, you're still required to maintain a model to make predictions. And you definitely don't want to start from scratch every time, because that would be wasting a lot of computation. Can you think of some examples, applications where that can happen? Yeah. Stock market is one very important example where, again, as I said, the theory behind online learning can actually be used per actually be used and is used in various models. Okay, in the sense that you get your market fluctuations today, and based on that you refine your model a little bit for predicting tomorrow, and based on the outcome, how much win or loss you have, and some other factors, you make some adjustments to your model and keep repeating this process. It's almost like a continuous learning process, right? You're continuously refining your model, and you want to aggregate your errors in some way. What are the examples? Yeah, autonomous cars are also like that. Okay, here, part of the reason, you're kind of in the scenario is that you encounter more and more sort of, outliers as you go along, and you want to refine your model to capture them. Okay, in stock market, it's even more inherent that you have to work in an online fashion. Any other examples? Well, one example is definitely poker. If you're playing a game of poker, in some sense, you're trying to adapt your strategy as the rounds go along to your opponent's play, right? Maybe you think that they're more aggressive, try to learn their behavior and then try to adjust your own strategy according to that, right? And another sort of very important commercial application is online advertising. Okay. Depending on what you click now, the ads that I see on the next page will be different. So somehow, based on your click-through rate on your history and what I've been clicking on, the model is kind of adjusting itself and can change what it's going to show to you, right? So these are all applications which sort of fit into the scenario where we're not seeing the data all at once. And we had to, but at the same time, we still have to keep making predictions. We can't say, okay, I'll wait till, whatever time until all of the data is collected, and only then will I make my model. Okay. So how do we address this scenario? Right. So when we talked about the basic model for learning, we could set it up as a simple optimization problem, but how do you do it for online learning? Okay, so let's talk about that a little bit, and then it will lead us to another sort of, some other optimization problems, and then we'll talk about that. All right. So the setting, how we will model it is as follows. There are various versions depending on how much assumptions you're willing to make. But let's just say, let's start with the simplest one. So on day one, think of you're playing a game, right? Each day, you get one example, X1, and my model makes a prediction. Okay. You show me the data from, whatever news from yesterday. I make a stock market prediction to say whether or not the index is going to go up or down. Okay. And based on that, this is my sort of example. This is my prediction. And then the truth is revealed. Right? This is the true label. Okay, let me put this in the superscripts. Okay. So you have an example, you have a prediction, and then the ground truth is revealed after you make the prediction. Okay. And the loss or cost for us is going to be the distance between the prediction that we made and the truth, which is the same thing that we did earlier, right? We are assuming that there is some loss function which measures how far our prediction is from the actual true value. And this is our loss event. Okay. So you're playing this game again and again, maybe for day 2, it's the same thing. I get x2, and then I make a prediction, and then the truth is revealed. So this is example, prediction. And again, when I say truth, it's just the true label. It's not as if there's an underlying ground truth, but that's the label that was observed. So on and so forth. Okay. And you keep playing this game forever, right? So the question next is how to compare different models. How can we compare different models? Right, I have a model 1, which makes some predictions and then gets some score, whereas someone else has a different model which makes different predictions and gets different sort of scores or loss functions. Which one would be better? What would be a quantitative way of comparing these different models? Any suggestions? Yeah. That's a good starting point. So let's say weighted sum of losses, across time, right? Okay, but then we have to be more precise about how are you going to weight it, right? Are you going to say, okay, maybe the, on loss on time t, I don't care that much about what happened like, 10 years ago or something, or should I only care about what's happening like in last year? Or should I only look at the entire history and look at the average for each day? All of these are sort of, choices that we have to make in how to target our learner, right? Any other suggestions? Yeah. Right, sample complexity to what though? Okay, so that's a good point too. So let's say that, imagine there is actually a model which can get 0 error at some point. There is some underlying ground truth. So there is some ground truth, which is, y is f star of x. And then you can say, how many samples till you stop making, how many samples or how many days till you stop making any more mistakes. Okay, this is almost good, but even within this, even within this way of accounting things, different schemes could be better or worse, right? Maybe 2 models stop making mistakes on the same, let's say the 1000th day, but one model only makes 1 mistake in these 1000 days, whereas the other model makes 1000 mistakes. Right? And the first model would be better, right? So we would like to even count, maybe even if there's an underlying ground truth, we would like to know when will you stop making mistakes? Okay, and how many mistakes did you make in the entire run? All right. So there are many different ways of quantifying this online learning, and each one has its own benefits. But we will look at 2 ways of quantifying how good a model is. Both of them are related. The first one will be a little bit easier to optimize, but it requires a stronger assumption on how the data is being generated. Okay, and then we'll relax this assumption to find something which is a lot more realistic and is much more widely applicable. Okay, So the first target is going to be under the following assumption. So I'm going to say that we have some there is some hypothesis class H, just like we did in ERM formulation. We said, okay, just look for the best predictor in some class of predictors. And we had to make some assumption about where you're going to look for. This could be linear functions, this could be deep neural networks, it could be anything. Okay. Now we're saying we have some hypothesis class H, and there is and there is some F star in H such that Y is actually equal to F star of X. Okay. The true label is actually equal to some underlying function evaluated on the example. We don't know what this function is, of course. We have a guess as to what the class is, but we don't know what F star is. Okay. But the true label is actually equal to it. All right. So now you can, and for simplicity, let's also assume that the labels Y are just 0, 1. Okay. And we will relax this assumption soon once we have some algorithms that, and once we'll develop some algorithms under this assumption. Okay. And then we'll relax it to general real valued losses. So, okay. All right. So what is the game we are playing then? We have some day 1, you see some point x1, you make a prediction y1 hat, and then you see the true label y1. Okay. And let's say loss is 1 if okay. So just think of stock market prediction, right? I'm trying to predict if the index is going to go up or down that day. Okay, very simple. Once we can do that, you can try and even guess how much it's going to go up, how much it's going to go down. But let's just try and guess the direction first, right? Is it going to go up or is it going to go down? And there is some underlying model which is able to get the best or the right direction. And we'll say our loss is 1 if our prediction is off. We said up, but the market went down. That means you get a penalty of 1. Okay. And the same thing on day 2 and so on. Okay. And the way we will compare different prediction algorithms is, to start with, we will use what's called the mistake bound. Okay. The mistake bound just asks the following. Okay. So in the mistake bounded model, what you're looking for is an algorithm that is going to make a bounded number of mistakes no matter how many days you play. Okay. So why is this different from the usual learning, right? Why is it not the same as saying that I want to learn F star? My claim is that, when I say, okay, your goal is only to find an algorithm that's not going to make more than, like let's say 100 mistakes, no matter how long you play this game. That is different from learning F star. Any conceptual reason why you might think so? So the fundamental difference here and kind of the learning formulation that we looked at in the first lecture is that now I'm not making any assumption about the distribution of the xi's. Right? Remember back when we started talking about learning and empirical risk minimization, we said your test should be similar to your training, otherwise it's not a well-posed problem. But now I'm kind of not allowing or not making that assumption. I'm just saying you can show me whatever you want on the 100th day, 101st day, and so on. I'm not going to assume that what you're going to show me next is related to what I saw earlier. But in the end, I'll stop making mistakes. Okay, so in that sense, online learning is stronger, or is assuming something weaker, which is that there is no connection between, there's no assumption on where these xi's are coming from. Okay, sounds sort of weird, right? That you should expect such a thing. Okay, but intuitively it is plausible. The reason being that if you show me new things every day, eventually you'll show me enough information to learn F star. Whereas if you keep giving me the same old examples, I'll just memorize them and answer them perfectly. Okay. It's like, let's say you're playing poker, then I might have different strategies, but if I just playing the same strategy every time, you learn my strategy. Whereas if you keep doing something random, then, I'll do something. Okay. All right. It sounds somewhat, sounds difficult to believe that you can do this without any assumption on the distribution of the xi, but as we will see, you can actually do this. Okay. As an example, let's look at a classical algorithm in learning for half spaces. Okay. So here, the hypothesis class H is going to be half spaces, meaning, just imagine that I have some line, right? And all points on one side are going to be labeled +1. And all points on the other side are labeled -1. Okay. So F star of x is equal to 1 if there is some weight vector W star such that, if the inner product between the two is greater than or equal to 0, I output 1. Otherwise, I output 0. Okay. So the greater than or equal to 0 could be, greater than or equal to some threshold, but let's just make it 0 without loss of generality, just kind of reduces the number of parameters. Okay. It's a little bit like saying, my weights, my W star could be weights for your different assignments and your exams. And I take the weighted sum. If it's more than like 80, you get a pass. If it's less than 80, you get a fail, something like that, right? It's the same kind of setting, but I've just normalized it so that I'm comparing against 0 as the threshold instead of some other number. Okay. And so we'll assume that your true label is being computed like this. Okay. So now let's revisit our learning problem. We see examples of the form, I shouldn't say like that. So let's say day 1, you see some x1. You make a prediction y1 hat, and the truth is revealed. Okay, let me just say sign, meaning, if it's a positive number, I output 1. If it's a negative number, I output 0. Right? And you keep repeating this, on day 2, once again, I see an example x2. Now you make a prediction, then the truth is revealed. So on and so forth. So you're playing this game, ad infinitum, and you have to make as few mistakes as possible. Okay. Can we have an algorithm that makes a bounded number of mistakes? Okay. So there's no underlying distribution or any such assumption. We just want to make a bounded number of mistakes. All right. And what we will do next is to come up with an algorithm for this problem. And it's a very classical algorithm. And to define what the algorithm is and what it does, I want to introduce an important notion in statistical learning theory called margin. Okay. So if you look at this picture, I just said that you're assuming that, there is a function f star, which is like a weight vector w star, such that, whenever the weighted sum is more than 0, you output 1. When it's less than 0, you output 0. Okay. But things, if, the points can get very close like this, that would be a harder problem to solve than, if you have some sort of margin for error. Okay. If there is a margin for separation, that should be an easier problem to solve. Okay. It's a little bit like saying, if you get 80, you get a pass. If you are 79.99, you get a fail. That would be too rigid, right? So we're also going to make the assumption that not only do we have a weight vector, which kind of gives you a classification like this, but the classification is also somewhat robust. Okay. Meaning there is a small band. There is a band that separates the positive and negative examples. Okay, so we have some margin of separation between the positive and the negative. We have some margin for error in this weight. Okay. So in that sense, I think it's a fairly intuitive notion that, not only do you have a weight vector, but kind of does the separation in a meaningful way. It's not very close to the boundary, right? So pictorially, you should just think of it as kind of, there's a slab of width roughly gamma. Gamma is the traditional letter for denoting margin. And there is no point which is this close to this separator, right? You have the separating line, And you don't have anything which is very, very close to the line. Everything is above it or below it. Okay. So how do you define this margin? So margin is I'll first write down the equation and then describe it. Okay. So right, so this is the origin, and this is our W star. Okay. So you want to say that no point is very close to this line, right? And how close you are really depends on the angle that you make. Right, so this is my X. We want to say that the angle between like the separating line and X isn't too small. If it is too small, then you're very close to the boundary, and that's what we are going to assume. Okay. And so this is what it quantifies. This is the angle between W star and X. We're assuming that the angle is always at least something. So you are not kind of lying in this band. Okay. And to make things a little more easy quantitatively, we can assume that W star as unit norm, and assume without loss of generality that all of our examples are also of unit norm. Okay. So we are only looking at the weighted sum, right? So whether the weighted sum is positive or negative. So if I just scale things up, the sign is not going to change, right? So let me just scale things up so that everything is of unit norm. And then the margin is the minimum or all of my data points of W star comma X. Okay, I should say all data. Okay. So the minimum inner product is at least something. And under this assumption, can you stop making mistakes quickly? All right. And we'll see that this assumption is enough to get an algorithm. And in particular, let me say, there is an algorithm so there is an algorithm that makes at most 1/gamma squared plus 1 mistakes. Okay, no matter how many days you run this algorithm, as long as you have margin, it will only make at most 1 over gamma squared plus 1 mistakes. Okay, there's no dependence on time, there's no dependence on the dimension, how many days you play or the dimension, as long as you have this guarantee that the points are not very close in this band. Okay, any questions about the statement of the theorem that we're going to show? And as we'll see, the algorithm is also going to be very simple, and it's also an important one. Yeah? Gamma is this margin. It's just a number which quantifies how much separation you have between the positive and negative points. One way to think about this is, what's the distance, the minimum distance between the positive and the negative points? Now, if you imagine that the positive and negative points can be very, very close, then your separating problem should be much harder, right? There's a smaller line, smaller space for you to thread the needle, whereas if the gap is bigger, you have more room, so it could be an easier problem to solve. Yeah? Yeah, so we are assuming some universal bound on the total margin that you're ever going to have. But under that assumption, you're not going to make any mistakes. Okay. And there are versions where you can make it depend on the effective margin and distributional margin and so on. But we're going to just consider the basic version and use that as a motivation to look at an algorithm. Okay. Any other questions? Okay. So let's take a 5-minute break, and when we come back, we will look at this algorithm. All right. So the algorithm that we're going to look at is called you might have heard the name before. It's called the perceptron algorithm. Okay, and this is from 1958 due to Rosenblatt. I can actually here. Because there's another connection. No? Right. Okay. So what's the algorithm? The algorithm is actually can be explained fairly intuitively. So remember our assumption that all of the data points, we just scaled it to be to have unit norm. So let's say this is a unit circle. So every point is on this circle. Okay. And our unknown W star is this. Right? So that means that every point on this side of this line is labeled +1, on the other side is -1. Okay. And initially, maybe we start from this point, which is W0. Okay, so we are starting from some point, W0, and we'd like to make progress one way or the other. Okay. So W0 is our random vector. On day I, we use our current best guess for what W star is to make a prediction and just make a prediction according to that, right? So compute sine of Wi comma xi minus, sorry. Okay. So on day one, we are going to use W0, just compute the inner product. If it's positive, output 1 and predict otherwise output 0. Okay. Okay. So you made this prediction and then the truth now you see yi. Okay. So what should you do once you see the true label after you make the prediction? Okay, so let's say your prediction and the true label agree. What do you do then? Any guesses? Well, think a little bit lazily, right? Why change something when it is working? You made a prediction and your prediction was correct. So why do you even have to change the model? So we'll just be a little bit lazy or strategic and say, my weight vector for the next day is going to be the same if no mistake. If I didn't make a mistake on a day, I'm not going to update my weights. I have a guess as to what the reality is. Whether it's true or not, it didn't make a mistake, so I'm just going to stick with it. Okay. But the interesting case is when you do make a mistake. Okay. So if these two are the same, then you're good. But if they're not the same, then you want to update your weights somehow. Right. So it's basically like, there's some life knowledge here in that mistakes teach you more than, just being right all the time. You learn more from your mistakes. So, this is your W0. So what is the error region between the blue hyperplane and the black one? Right? You make a mistake when you're in this region, right? My point xi is over here, then both of my, the true label, true weight vector, and my current guess for the weight vector both say positive, so I'm good. Okay. Whereas in this arc, both say negative. So once again, I won't make any mistake, right? So I only make a mistake when my point x is, kind of, let's say here. It's either in here or here. So let's say it's over here for now, okay? So how should I update my weight vector once I made a mistake? Any guesses? Again, just think intuitively, right? I know that I don't know what W star is, but there is some hidden picture like this. I made a mistake and I want to update my weight vector in some way. Which way should I move my weight vector? Okay. Maybe we can break it up a little. So let's say yi is positive, but we said negative. Okay, so meaning the true label is positive. It's on the positive side of the cyan colored hyperplane, whereas we've said, we gave it a negative score. So which way should I move my weight vector based on this information? Guesses? So even from this picture, my W0 is here, but my Xi is kind of in this arc here, right? So moving towards Xi is going to get me closer to W star than where I started out with, intuitively. Okay, so the true label was positive, but I'm kind of pointing away from it. So it makes sense to move towards the Xi. Okay. So my algorithm is just going to mimic that intuition. So when I make this kind of mistake, for the next day, I'm going to set my weight vector to be my current weight vector plus Xi. Okay. So I'm trying to move towards, I guess, maybe let me draw it this way. If I move in this direction, I'd probably make progress to W star. Okay, again, this is just our best guess for which way does W star lie. Okay. On the flip side, what if I make the other kind of mistake? I thought the label was 1, but the true label came out to be negative. Okay. So that means we are in this scenario, right? So we are on the opposite side of W star, but we thought it was on the same side. So we made a mistake, which is a false negative. Okay, so we are here. So in this case, how should I update my weight vector? Any guesses? We should move away, right? Again, somewhat simplistic intuition, but let's try it out and see what happens, right? So we're just saying in this case, you should move away. Okay, so that's the perceptron algorithm. When you make a mistake where the true label is positive, but you call it a negative example, just move towards that example. Okay, and do the opposite in the other case. And if you don't make any mistake, no need to change anything. Okay, and a succinct way of kind of writing this case analysis you can check is to say this formula. Okay. Doesn't matter, it's just a succinct way of writing it, because if yi is positive, I'm just getting 1, whereas if it is 0, I'm subtracting. Okay. So that's the perceptron algorithm. And the simple theorem that we'll show is that so as long as you have margin gamma, meaning W star gets some good kind of separation, then your perceptron algorithm is not going to make too many mistakes. Okay. So let's prove it. First, I want to say this is quite remarkable because we're saying that the number of mistakes doesn't grow forever. No matter how long you run it, you're only going to make a fixed number of mistakes. And that does not depend on the dimension. It only depends. You might be working in a million-dimensional space, but as long as I know that the positive and negative examples aren't too close, I'm only going to make a fixed number of mistakes. Okay, so this independence on dimension and the time is kind of very, very nice and somewhat rare. Okay, it comes from making the strong assumption of margin. Okay, you had a question? Yeah. Right. So technically we need to, but just for analysis, I'm not going to. But the algorithm would not change too much if you keep normalizing. So because we are only looking at the sign of the inner product, right? So we can scale and rescale without changing the sign. Okay. And there is a version of it where you can renormalize after each step, but it's easier to implement it and analyze it without the renormalization. Okay. All right. Okay, so how do you show such a thing? Well, what you show is that every time you make a mistake, you learn something about W star. You make some progress towards the true W star, which was our intuition, right? We said when you make a mistake, you take a step in the direction of W star. So you kind of say, okay, my angle towards W star is going to increase. Okay. So when we make a mistake, what happens? Well, we have okay. So let's see, does the angle between W star and my vector improve or not? Right. So this is the inner product between my current guess for the weight vector and the true weight vector W star. Okay. So now think about this expression here, right? So when W star has a positive inner product with xi, what is this number? It's 1, right? Because yi would be 1, right? When this inner product is negative, what would this be? It would be -1, okay? So whether or not the inner product is positive or negative, the overall product is positive, right? You're just putting the right sign in front so that, when it's, when the weighted sum is positive, I'm adding it. When the weighted sum is negative, I'm subtracting it, right? So either way, I'm going to increase it. So let me write it as the absolute value of the weighted sum. Okay. I'm kind of making sure that my angle always increases. That was our intuition in the first place, right? We said you move towards the W star, okay, which is kind of being evidenced in this equation. Okay. And how much does it increase? It's always increasing, but is there an amount by which we can guarantee? Any guesses? Like I want to say that you're not only increasing, but you're actually increasing by at least something. The margin, right? We said that the inner product is at least something. That was our assumption on margin. Okay. Okay. So that means for every mistake I, so every time I make a mistake, I increase the angle between my current weight vector and W star. Okay. And we will now couple this with another claim. So if I just wanted to increase the angle, somehow it can be trivial, right? I can say every time you make a mistake, you increase the norm or just scale the weight vector some way. That can also achieve this such an equation. Okay. So to complement this, we are also going to say that while we are increasing the angle, we are not growing our vectors too fast. Right? So what do I mean? My weight vectors, their norm increases by at most 1 in each round. Okay. Why is this? Well, you can view it by a picture really. This is Wi minus 1 and okay. If no mistake, in round I, nothing to prove. Right? If we didn't make a mistake, there's nothing to prove because we did not change the weight vector. So in particular, you did not increment its norm. The weight vector remained the same. So we only have to worry about the case where you actually made a mistake. Okay. But when you make a mistake, the update equation said something like this. Okay, so this is our update equation. And okay, let me just draw a bigger picture. So this is Wi minus 1. And this is going to be this term. Okay, so we're going to use some elementary sort of, vector algebra to say, okay, the norm of the sum is going to be at most the sum of squares of these two norms. Okay. Why is that true? Well, it's basically going to be true because the angle, as we will show, this is an obtuse angle. Okay, it's not kind of going towards, it can go at most, this is an obtuse angle, so you'll get an inequality, but let's work through it carefully. So if I use the cosine formula again, the norm squared of Wi is going to be so remember this part is 1 or minus 1, right? So we just, it was just our shorthand for 1 or minus 1. Okay. So if I use the cosine formula, I get Okay. So for any two vectors v and w, the norm squared of the sum is at most the sum of squares of the norms plus twice the inner product between the two vectors. Okay, so we're just using that. And this is just, what we had earlier. The norm of each example, we said by scaling is at most 1, but then we have this additional term that we have to figure out. Okay, so this 2 times yi minus 1, that's just a scalar. And then you had this. Okay. What can you tell me about this last term? Any suggestions, guesses? Well, think of how our algorithm proceeded, right? So we only updated it when we made a mistake, right? So if yi equals 1, right? If the true label was positive, then we should have predicted 0, meaning the sign was actually negative, right? Otherwise, we wouldn't have made a mistake. We wouldn't have made an update. Okay. In the same way, if yi was actually equal to 0, then was positive. Okay. So what does this tell me about this last term? It tells me that this last term is always negative, right? Because, if this is 1, that means the first part is positive, but then the next part is negative. Okay. So implies all right. And in the same way, so these two must be of opposite signs. That's what we're saying. When you made a mistake, means that your prediction was opposite to what the truth was. So the angle should have been obtuse. Otherwise, you would have not made a mistake in the first place. Okay. So this implies that each time you increase the norm at most by at most 1. Okay. So let's put these two things together. So far, we know that every time we make a mistake, we increase the angle with the unknown true weight vector. But at the same time, the norms never grow too much. Okay. So how can I use these two? Well, suppose we played the game for some number of days, for some capital T number of days, and we made capital M mistakes. Okay. So this implies that the total norm of our predictor at that point is at most 1 plus capital M. The norm squared is at most 1 plus capital, right? If you don't make a mistake, the weight vectors don't change. If you make a mistake, it grows by at most 1. Okay. And on the other hand, we also know that this inner product is at least what you started out with plus m times gamma. Okay. So every time you make a mistake, the angle increases by gamma. So if you made capital M mistakes, you must have increased it by at least this much. Okay. So now we use Cauchy-Schwarz to say the inner product between two vectors is at most the product of their lengths. Okay. For any two vectors, their inner product is at most the product of their lengths. Right? So this is less than or equal to square root of 1 plus capital M. Okay. Any questions? All right. So now I'm in good shape. And I just have to do some arithmetic to say I have m times gamma is less than or equal to 1 plus capital M minus the starting and I'll use the same inequality again, that the inner product between two vectors is at most the product of their lengths. And then since I'm starting with a unit vector, this initial angle can be at most 1. So what I'm subtracting is at most 1. Okay. So you get some sort of quadratic inequality involving the number of mistakes that you made. Okay. And the weird thing here is that this inequality doesn't depend on time at all. It's just saying that if m is the number of mistakes you made at any point, it must always satisfy this inequality. Okay. And you can do some arithmetic from now on to say that this implies, after some quadratic equation solving, okay. So you have to solve some quadratic equation to figure it out exactly. But intuitively, as m grows a lot, here you're growing linearly, whereas here you're only growing with the square root. So m cannot be too big. Okay, in particular, when you are here, you hit kind of a contradiction. So you must satisfy this inequality. Okay, I'll skip this calculation, but the main crux of the argument is to show that whenever you make a mistake, you make some progress towards the true unknown W star. Okay. And the progress is coming really by increasing the angle and not just by scaling your vector in some arbitrary way. Okay. And it's also a proof of concept that you can actually get this mistake bounded algorithms under some realistic assumption. It's a strong assumption, but you're just saying, okay, not only do I have like a nice classifier, which is like this weighted some, but it gets a good separation between the positive and negative examples. Okay. The margin assumption is fairly strong, but also, I think quite useful to make in many scenarios. Okay. And what we'll do in the next lecture is, study this problem of online learning and go beyond this strong assumption, right? So we said there's a true model which has a margin, and under these assumptions, we can get a mistake bound on the number of mistakes our algorithm makes, okay? But it might not be the case that there is such a strong assumption to make always. What can you do in those scenarios? And we'll see that even then, we can get some pretty good guarantees for online learning. So that's what we'll talk about on Wednesday. And remember that assignment 1 will be out today at 10 p.m. Okay, it should be up on Gradescope. Okay, all right, I'll see you all on Wednesday.